All right, so this is part 2. So let's walk through a couple cases. Oh, do I not? Hopefully there's enough room. Okay. So let's say you have a nozzle and it shoots stuff out with a pressure that's greater than P ambient. What's going to happen? Well, the exhaust will go like that, and then it'll spike up. And it'll spike up so much that it'll actually end up going down and then coming back up and going down and coming back up. And you'll see like diamonds in the exhaust. You can Google it, like Google videos of it, and you can actually see those diamonds. So it'll overexpand, underexpand, overexpand, underexpand. And that's just because it overexpands too much, and then it gets too low of pressure, and then ambient pressure pushes it back in, and then it pushes it too much, and then it re-overexpands, and each time the magnitude will decrease, and eventually it'll like stable out. But yeah, that's kind of what's gonna happen. The bad thing about it is to expand, some of the velocity is in that direction, and you don't want velocity in that direction. You want all of the velocity in that direction. And that's because the thrust, m dot v, is proportional to v. So you want v to be as big as possible. So you want all the velocity to be shooting it backwards. You don't want any of the velocity to be wasted pushing it up or pushing it down. Cool. Likewise, if you have P is less than P ambient, it'll go up, and then it'll immediately shrink and then expand and shrink and expand. So it's the exact same thing, just backwards. And it'll eventually like stabilize out. And again, some of the velocity is in that direction. And you don't want that because you want all of the velocity to be shooting straight backwards. And the way you do that is by always having the exhaust pressure equal to P ambient. And the way you do that is, like we talked about in the last video, you control the area as the rocket's going up and up and up. You control the area. Okay. So what happens if you overexpand it let's start with the underexpand. What happens if you underexpand it too much, where P is super, like way higher than P amp? It'll like spike up and just go out like that, right? And that sucks because like instantly you're losing a lot of the velocity to the right to like upwards. You're just losing all of that velocity, and that sucks. But what could be even worse is if your P ambient is much, what would it be? Is much, the wrong pressure. Pressure is much less than P ambient. It'll shrink so much that it will cause a normal shockwave in the exhaust. And normal shockwaves suck because they reduce the velocity. So V1, V2, you're going to get that V1 is greater than V2. So in this case, I don't think it'll send any of the velocity like up or down. I think all of it will still stay in that direction, but it freaking decreases the magnitude just straight up, which you don't want. So there is a case analysis for this. So this is my plot. You have pressure, you have stagnation pressure, and you have the choke. So it would decrease down to the choke, and ideally it would decrease even more and then go out the exhaust at P ambient. Right at P ambient, not any different. And you control that again by controlling the area. But what could happen, like we talked about, is you could end up with a normal shockwave. I'll draw it a little taller in the exhaust. That would, like we said, that would decrease the velocity and it would increase pressure, which is why it went up. And you could also have another case where it just won't go fast, like it'll reach Mach 1, at the choke, but then it'll decrease back down to like a Mach that's less than 1. Yeah. And we call these, I'm gonna erase that for now. This is called case 4, and this is called case 6. This is called case 3. There are a couple other cases also, and those cases are that you have a normal shockwave right here. I drew it. You have a normal shockwave right at the exit, but you could have it somewhere earlier. And I'll explain how we calculate that later. But that would be case 5. And you could have it so there's not enough difference in pressure to cause a normal shockwave, and that, but it's not right at the design condition, like it's between case 6 and case 4, and that would be case 7, and this would be case 8. And both case 7 and case 8, those were like the diamonds I was talking about earlier, where it'll like look like that. Like that, right? Those are case 7 and case 8. One of them, the diamonds would go up, and the other one, the diamonds would start by going down. And again, you can avoid all of this if you perfectly control the area of the nozzle. So which of these can we objectively calculate? I didn't write this case number. This is case 3. We can calculate 4, 6, and 3. Cool. So how do we know if it's a case 5 or a 7 or a 8? Well, we kind of just say if it's not this exact number and it's not this exact number, then it's case 7. And if it's close to either a case 6 or a case 4, then sure, we could say it's one of those. But if it's somewhere that's like way in between them, then it's a case 7. So to do this, you need to know how to calculate normal shockwaves. And it's very similar to these equations, like very similar. Exact same idea. So if you understood those, you'll understand this. So that's that one. They look very abstract and weird. And that is because they are. But this is what they are, and you literally can't avoid using them. Oh. All right. And the last one. I'm gonna write it a different way. I'm gonna just square root the right-hand side. Okay, so for all of these, what do you need to, well, okay, let me draw a nice picture first. So you have a normal shock, and state 1 is on the left side, and state 2 is on the right side. So P1, T1, M1, P2, T2, M2. And I believe if you do them, well, you should get that the M dots on both sides are equal. I think that's part of the derivation of this. But anyways, if you know these three, you can calculate all of these, like all of them. Because for the pressure equation, if you know P1, you know K, you always know K. You know M1, you can get P2. Same with T2, and same with M2. Yeah. So the way this works is so before I mentioned it's possible to have a normal shock in the exhaust and right at the end. So why would it be in the exhaust? So here you have P stag, and here you have P star, and here you have P ATM. And well, technically PATM is surrounding. But right at the exhaust you have, what do I call it? P design. Yeah, I'm gonna call it P design. So as we showed with this plot, the pressure just goes down. It starts high, then it goes lower, and then it goes lower. Ideally, if you're at a case 4. So what do you need to do here? So it's been a while since I did this, but I believe the right way to do this is, you know, PATM, plug that into into P2. You know M1 because that's the case 4 M1. That's the case 4 M1, so the design M1 that you get from this equation. You know K, so you can calculate the pressure. And that would, if you have a case 6, that pressure would be, if you have a case 5, that pressure would be somewhere between here and there, because the pressure is decreasing. So it'll be somewhere between those two. Now, for a case 6 where it's a normal right at the exhaust, the way you would do it is using your normal equations. You would get, you don't even worry about PATM to start with. Typically, they'll give you the area ratio. So they'll give A star, they'll give A, and then you can calculate the Mach number, and then based on that, you can calculate the pressure, this pressure, and then based on that, you plug that in as P1, and you plug in the Mach number that you have, and you get a P2. So you literally write the numbers. Like you would say, maybe you start at like 600 kPa, and then case 4 is like a 20 kPa, case 6 is like a 50 kPa, and case 3 what would case 3 be? Kind of forgot how to do the case 3. It was pretty easy though. I forgot how to do it, but it's not that important right now because you almost never see it. But yeah, you literally calculate those numbers, and then if it's between a case 6 and a case 4, then you know it's a case 7. I'm gonna clean these up a bit. But yeah, that is pretty much it. This is really important. You always want to be at case 4, and again, you can do that easily if you can control the area ratio. Yeah. And normally the way the problems, like academic problems that I've done, work is they give you the stagnation pressure and temperature and whatever, sometimes even just the stagnation pressure. If they'll give you the temperature if they're asking you to solve for thrust, because you need it for that. But if you're just asked which case are you at, then all you need is pressure and ambient pressure. So you'd use that. You'd use the A over A star that they give you, and then you'd calculate the Mach number, and then with the Mach number, you'd calculate the pressure, and then that is your case 4 pressure. And then with that case 4 pressure, you assume that's P1, and you plug in your Mach number, what I just erased, you plug in your Mach number as M1, and you get a P2. And that P2 is the case 6 number. And then case 3, I kind of forgot, but it doesn't really matter. But that's about it. So the main things I would write down are this whole picture. This is not A star. And I would write down these equations. And if you want to write down this picture, go ahead. Again, fluid flows from left to right. And if you want, you could also just prove to yourself that velocity decreases as you go through a shockwave, and you could do that with the MC square root KRT. And you could get the M with this equation, you can get the T with that equation, and you're chilling. But it does decrease. And again, you don't want it to decrease because lower velocity is lower thrust. So you want to avoid that. So far, I'm gonna erase these as well. And these lines. I'm gonna make this as clean as possible. Cool. Cool beans. That is literally it. That is all of Nozzle design. Next, I'm gonna do oblique shockwaves and expansion fans. And those are both very important for aerodynamics. Not so much nozzle design, but yeah. Cool beans.